Alrighty, hey guys, how's it going? So we are going to finish up. I'm going to give you the last of your information in these next few videos that you're going to be watching on Edpuzzle, and that'll be it for this year. Can you believe it? Cool thing about this is that we've actually already done exponential functions and logarithmic equations. This is technically section 3.1 in your textbook. So if you want to make a note down, we did do this during the first semester. So quick reminder, a recall of your parent function. So we could have, now the parent function is dependent on what we want to have on our exponential function. So first of all, an exponential function is something where I've got the variable x in the exponent spot. So it could be y equals 2 to the x, or of course you could, write it in terms of f of x equals 2 to the x. So that would be a parent function. And if we were to graph it, remember that if I'm going to have x going to, if I plug in 0 into x, I would have, just remind you of the table of values over here. So if I were to plug 0 in, you'd have 2 to the 0 power, which of course is 1. If I were to plug in 1, you'd have 2 to the first power, which is of course just 2. If I were to plug in 2, you'd have 2 to the second power, which is of course 4. And so on and so on. And my graph would just continue on in this direction up here. And then if I were to plug in negative numbers, like say -1, I would have 2 to the negative first power, which is of course 1 over 2 to the first power, which is a half. If I plugged in -2, that would be 2 to the -2, which is 1 over 2 to the +2, which is 1/4. And if you think about that end behavior, which is what we just did with limits, if I continued to let x go towards negative infinity, I'm going to just keep leveling off and getting closer and closer and closer to a y value of 0, which means I've got a horizontal asymptote at y equals 0, which is a horizontal asymptote. I'm only approaching that horizontal asymptote when x goes to negative infinity. When x goes to positive infinity, then this would be infinity. So if I just went back to what I just did with limits, if I asked you what is the limit as x goes to negative infinity of 2 to the x power, sorry, hold on, of 2 to the x power, what is happening here? Let me erase that real quick. Of 2 to the x power, then that limit would be equal to 0 because as x heads off to negative infinity, y goes to positive infinity. And if I did the limit as x goes to positive infinity of 2 to the x power, that would just be 2 to the infinity power, which would of course just be going to infinity, which you would also then always be able to say does not exist. By the way, congratulations on y'all's test. You guys did really, really well. I was really pleased. All right, so if we bring back in the limit stuff, then you can see that that's that end behavior. Now, if I choose to use, 2 to the x as my parent function, then of course transformations can all be, accordingly right there. So like I could take like y equals 2 to the x, -3, and that just means that that exact picture right there would shift down 3 units. So now, instead of having my horizontal asymptote at y equals 0, my horizontal asymptote would be at y equals -3, and my graph would look something kind of like this. So the thing about exponential functions is you have to realize that the parent function is dependent on whatever the base is that you've got. So that base can change. So let's say we wanted to graph something like y equals 1 minus 2 to the x minus 3. Because again, in calculus land, we could ask really about a limit as x goes to infinity or as x goes to negative infinity. So it's good to think about that stuff. So the transformations would be that we would move up 1 unit, because writing it like that would be the same as writing it as -2 to the x minus 3 and then plus 1. So we're going to move up 1 unit. We're going to move to the right 3 units. And then we are going to do a reflection across the x-axis. So we're going to move up 1 unit. Actually, I'm going to pause this so you can graph it. Okay, so there you go. So there's your graph, up 1, right 3, reflect across the x-axis. And again, the reason why it's helpful to have knowledge of logs and exponentials is because I could ask you a question like, what is the limit of 1 minus 2 to the x minus 3 as x heads to infinity? In which case you could see from the graph that this would be heading towards negative infinity. Or you can always say the limit doesn't exist if you're not approaching a specific number. I could ask you, what about the limit of 1 minus 2 to the x minus 3 as x heads to negative infinity? And in that case, that would be heading to a y value of 1. And then we have logarithmic functions, which are technically from section 3.2 in your textbook. So if you're looking to see where that's located, it's technically from there. And remember that when we find inverse functions, you would have to switch x and y values. So if I had something like the exponential function y equals 2 to the x, and I want to find the inverse, well, the first thing I would have to do is switch x and y. So now I would have x equals 2 to the y. But then after you switch x and y, you always have to then solve it for y. So then that's where I always say that little statement of a log is an exponent and a base is always a base. Hey, hey. So a log is an exponent and a base is always a base. Hey, hey. I know you remember me saying this all the time. So the base would be the 2. So 2 is the base. And the y would be the exponent, of course. And the word is over here means equals. So when I make the statement of a log is an exponent, I'm saying that a log is equal to the exponent. And then the base of the exponent is the base of the log. And then whatever else you've got, which would be the x, goes inside of there. So if I say something like f of x equals 2 to the x, then I could say that the inverse of f of x, which remember that's your notation for the inverse, is the log with a base of 2 of x. And so we already graphed a moment ago, we already graphed the f of x function, which looked like this, 2 to the x. So this is the function f of x. And then whenever we're finding an inverse, we always reflect over the line y equals x. So doing a reflection across the line y equals x gives me an inverse. And we would have, remember, we would have normally had a horizontal asymptote of y equals 0. When I do the inverse, I would now have a vertical asymptote of x equals 0. And my graph would look something like, I would switch all my ordered pairs. So instead of 0, 1, I now have the ordered pair 1, 0. And you're switching all of your ordered pairs around. So my graph would have looked something kind of like this. So this would be the graph of the inverse of f of x, which is the log. So this information right here is something that you kind of want to get into your brain. And again, the reason why is because moving forward into, you know, the next class, which is calculus, of course, you're not going to ever have to really be tested on a log or an exponential. Like, you're not going to ever be told, hey, here's an exponential equation that you need to solve directly, but you might have to solve an exponential equation to do the calculus. You might have to know what the graph looks like in order to do the calculus. So that's why we talk about this. So with logarithms, there's a lot of properties that go with them. So let's talk about things like what we would have. So the first thing is, if I ask you without a calculator to evaluate log base 4 of 1, well, that's where we have to remember that a log is an exponent and a base is always a base. Hey. So if I'm trying to evaluate this logarithm, I'm trying to figure out what this log base 4 of 1 is supposed to be equal to. So I'm going to, you know, try and figure out what this is supposed to be equal to. So remember that a log is an exponent. A base is always a base. Hey. So a log should be equal to the exponent. So this question mark thing is going to be the exponent. But that's what the log is equal to. The base is always the base. So basically what this is saying is 4 to what exponent would equal 1. So of course, hopefully you remember that any base, except for 0, but any number raised to the 0 power would always be equal to 1. So, sorry. So in order for us to be able to answer this question, I would need to know that the exponent would have to be equal to 0. So that means that log base 4 of 1 should be equal to 0. And so that's actually a property, is that a log of any base of 1 will always be equal to 0. So that's one property. Okay, but you could answer things like, what is the log with a base of the square root of 7 of the square root of 7? So again, we're saying that a log is an exponent, a base is always a base. So if I'm trying to figure out what this log is supposed to be equal to, then that's the exponent to the base of that square root of 7. So we're saying the square root of 7 raised to the exponent that I'm trying to find should be equal to the square root of 7 that's inside the log. Well, anything that comes out to be itself just means that that exponent, that question mark, should have been equal to 1. So that means that this is equal to 1. And so that's another property. Another property that says that if you've got a log of a base and whatever's inside the log is that same exact value, that will always be equal to 1. Okay, then we have bases that are the number e. So remember, e is just a number. It's about 2.718 and so on, so on. You can find it on your calculator. There's a number for it, or there's a button for it. So if I had a log with a base of e of, say, I don't know, 5, then you can also write that as ln of just 5. So if you ever don't write the base of e and you want to just be understood that it's a base of e, that's where you write ln. Also, if you ever just want to have, like, say, log with a base of 10 of, say, 100, then you could just say the log of 100. It's got to be log log, whereas ln is log with a base of e. So make sure that you understand the difference between those two. In calculus, we use natural logs. That's what these are called. We use natural logs a lot. And again, this should all be reviewed for you because you've done it before. Okay, then you can do something like, well, what if I've got the log base of 3 of x, and that's equal to the log with a base of 3 of 12. Well, if what's inside the logs aren't equal, but everything else is equal, like in this case, this is log base 3 and this is log base 3, then you can almost just ignore the logs and just say that, well, x has to be equal to 12 because that's what's inside the logs. Everything has to be equal. If you wanted to go with the properties of that, saying that a log is an exponent and a base is always a base, that'll add on another piece here. So we can say that a log is an exponent. So I'm going to just say that all of this is the exponent. So log base 3 of 12 is the exponent to the base that I already had of 3. So 3 raised to the log base 3 of 12 should be equal to the other thing that was inside of it. And there's another property that says that, I'll put it up here. There's another property that says that if you ever have a number raised to an exponent that is a log with the same base, then that will always just be equal to whatever's inside of that log. So a number, like in this case down here, 3 raised to a log with a base of 3, that will all just be equal to 12. Because it's almost like these things cancel out and you're just left with the 12. I'll give you a few more like important things that you've got to know. So I'm going to go back to just a basic exponential. So let's just make it any base to the x power. So your basic exponential equation will look something like this. The domain of that the domain of that exponential equation would be all reals. So I'm going to write an interval notation from -infinity to infinity. And the range would be all positives, so from 0 to infinity. When we find the inverse, we would have a log with a base of b of x, because the log is the inverse to an exponential. That's like the most important thing. And then when you find an inverse, all you have to do is switch around the domain and the range, because that's how you find the inverse. You switch x and y. So I'm going to switch around the domain and the range. So now my domain would go from 0 to infinity, not including 0. And my range will be all reals, so -infinity to infinity. And my graph would look something kind of like this. So it's very important to remember that inside of a log, if the domain is 0 to infinity, that's all positive numbers. So inside of a log has to always be a positive number. It can't even be 0, because that's the output you get from an exponential equation. That was the range. You'll never get a 0 or a negative unless you do a transformation where you shift the graph down. That's the only way you'd be able to get it. But just the exponential itself, which is, you know, the inverse is the log, inside of the log will always have to be a positive number. All right, I'm going to give you a few examples and finish up this video. All right, so first example. Evaluate log base 9 of 27.